Good day, grade 12 learners. Welcome to today's physical science lesson. My name is Mashudu Mamburo. This lesson is brought to you by Gauteng Department of Education in collaboration with Saibono Discovery Center. Welcome. Today we'll be focusing on knowledge area, matter and material, topic photoelectric effect. So we'll ensure that we do the entire topic and we do activities as well. But when we start our lesson, as always, we always start with the lesson objectives. These objectives, they come from the exam guideline to say this is what you are expected to know. When you say you are done with photoelectric effect, you must be able to know the following. The first thing, you must know photoelectric effect, how to describe it. You will see in the questions, we'll say define photoelectric effect. And the expectation there is that you will say photoelectric effect is the process whereby electrons are ejected. To eject is to remove. So we're saying it's a process whereby electrons are removed from a metal surface. A process whereby electrons are ejected from a metal surface when light of suitable frequency is incident on that surface. So it's very much important that you know how to define or how to describe the photoelectric effect. As you can look at the word itself, photo, which refers to light, and then electric, we're talking about the charges here, the movement of charges. So we are saying now is photoelectric effect, which means now is the process whereby electrons, the electric part, electrons are ejected from a metal surface. You will see that metals, they have those valence electrons that they're having, and then we are targeting to say when you bombard them with light, they must be able to absorb that energy from light, and then when they do that, they will be removed. So we're going to look at that to say what are the conditions for removal or for ejection of electrons from the metal surface. The second thing that we must look at is the significance of photoelectric effect. Do we use photoelectric effect in our day-to-day life? We have to look at that as well to say where do we do the application of photoelectric effect. The second definition, we must be able to define what is called threshold frequency. Threshold frequency, which is the minimum. A threshold is the minimum, is a minimum frequency of light. This frequency is a frequency of light needed to emit electrons from a certain metal surface. So for us to emit or remove the electron from the metal surface, we are saying that there's a minimum frequency of light that is needed. So threshold frequency is the minimum frequency of light needed to emit electrons from a certain metal surface. And then the third definition is we must be able to define what we refer to as work function. Work function, which is the minimum energy that electron in the metal needs to be emitted from the metal surface. You don't have to confuse the threshold frequency and the work function, because work function is the energy, while the threshold frequency is the frequency. So we're saying threshold frequency is the minimum frequency of light needed to emit electrons from a metal surface, and we're saying work function is the minimum energy that an electron that an electron in the metal needs to be emitted from the metal surface. So you can see that work function is the energy needed by the electron in order for it to be removed. So it means there is a threshold frequency, or there is a work function, which is the minimum energy that is required. It's not all the energies that are going to remove the electron from the metal surface. Now, after that, we've done three definitions. Remember, the photoelectric effect, threshold frequency, and work function. So I say at all times, remember these three definitions. And then you must be able to perform calculations using photoelectric equation. So our photoelectric equation in this case is given as like that, to say energy of a photon, which is E. We have done energy of a photon, remember, in grade 10. So as well, you will be utilizing that knowledge to say energy of a photon, which is E, is equals to HF. E equals to HF. So when we say photoelectric equation, we're saying now E equals to work function, which we said is the minimum energy required to remove or to eject electron from the metal surface, plus EK. So what are we saying here? We're saying that when we have this energy of a photon, it must be able to provide the minimum energy required, but all the other energy in excess, or the energy that remains after we have met the threshold or the work function, that energy must be converted to EK. So we are always going to compare the energy of light and the work function to say, are the two equal? Are the two, is energy of a photon less? Definitely, if it's less, there won't be removal of electrons. Is energy of a photon greater than? When it's greater than, definitely there will be a photoelectric or removal or ejection of electron from the metal surface. And then we're saying the energy that remains, if it's greater, if energy of a photon is greater than work function, we're saying all the other energy that remains will be converted to kinetic energy. So that's what we'll be focusing on. The other thing that you must be able to remember is that when you talk about the work function W0, we're talking about HF0, which means we can be able to calculate the work function using the Planck's constant H. Remember Planck's constant, the very same Planck constant you used when you were doing grade 10, when you were calculating the energy of the photon. We'll still be using Planck's constant, and when you multiply that by the threshold frequency, you are able to calculate the work function. So always you will check what you are given, because it will inform which formula you will need. So we're going to do that, and then we're going to look at the effect of intensity. When we talk about intensity, we're talking about the brightness of light. How bright or how dim is the light? What happens when the light is brighter, or when the light is dimmer? How many will the electrons be ejected, and what is the effect of that intensity? So we'll be looking at that, and as well we'll be looking at the effect of frequency on photoelectric, to say, as we increase frequency, what happens to the electrons that are being ejected. So we'll look at those effects of intensity. Remember, when we talk about intensity, we're talking about the brightness of that light, and we'll look as well at the frequency on the photoelectric effect. And we must be able to state that the photoelectric effect demonstrate the particle nature of light. Remember, light has dual nature. What does that mean? We're saying light can exist as a wave or as a particle. So that is the dual nature of light. So when we talk about photoelectric effect, we're talking about light as a what? As a particle. So the particle nature of light is what we're going to focus on. But light itself, it has dual nature, which is the light can exist as a wave and as a particle. And for photoelectric, we're talking about the light as a particle, the particle nature of light. So I hope you understand. This is what we're supposed to understand by the end of this lesson. And then we are saying it is important as well to talk to the issue of atomic absorption spectrum, and atomic emission spectrum. So you have done so much in terms of absorption of energy, like you have done endothermic reaction, you said energy is absorbed. You have done exothermic reaction, you said energy is released. Because these times we must not do it like it's separate stuff. We're still talking about absorption of energy and emission of energy or release of energy. When we're doing your rates of reactions and your chemical equilibrium, you're talking about exothermic as energy being released, endothermic as energy being absorbed. So we're still going to talk about now atomic absorption spectrum. What happens during this atomic absorption spectrum? We're saying the atomic absorption spectrum is formed when certain frequencies of electromagnetic radiation. So we're saying certain frequencies of this electromagnetic radiation passing through a substance is absorbed. So when some frequencies of our electromagnetic radiation is absorbed, when passing through a substance. So we're saying when this electromagnetic radiation, EMR, when light is passing through, because that's our light, when light passes through a substance, there will be the certain frequencies will be absorbed, and we refer to that as atomic absorption spectra. So for example, when light passes through a cold gas, remember light is saving energy of a photon. Within light we have energy of a photon, what you will refer to as a quantum for singular or a quanta for plural. So you must be able to know that we're having this light that passes through a cold gas. Atoms in the gas absorb the characteristic frequency of the light. So some of these frequencies will be absorbed by the gas itself, the atoms in the gas. And the spectrum observed is a continuous spectrum with dark lines. So there will be continuous spectrum with dark lines where characteristic frequencies of light were removed. The frequency of the absorption lines are unique to the type of atoms in the gas. So it will depend which atoms do you have in that particular gas. So we're saying when light or when the electromagnetic radiation passes through a cold gas, the atoms within that gas will definitely absorb certain frequencies of this electromagnetic radiation. So hence we define atomic absorption spectrum. I'm emphasizing because these are some of the definitions that we find that learners, they don't take them serious, and they are asked and learners are unable to respond to them. So I'm saying you must be able to know atomic absorption spectrum as certain frequency is formed when certain frequency, so you'll remember certain frequency of electromagnetic radiation passing through a substance, passing through a substance is absorbed. So certain frequencies of electromagnetic radiation passing through a substance are absorbed. Please remember that definition of atomic absorption spectrum. I've indicated that is when now our electromagnetic radiation or when our light passes through a cold gas, and we're saying there are atoms within a gas, and those atoms will absorb that energy, that frequency of light, and the spectrum observed will be continuous spectrum with dark lines where characteristic frequency of light were removed. Now you are able to see that. Now let's look at atomic emission spectrum. Atomic emission spectrum, as the word says, emission. You can see that now we're not absorbing, but we're releasing. It. So what is happening is formed when certain frequencies. So the main thing is that we must have certain frequencies of electromagnetic radiation. That's what makes these definitions easy. Hence, the main thing that you got to remember is that here we're talking about certain frequency of electromagnetic radiation. In this case, they are not absorbed. Remember, with absorption spectrum, we say certain frequencies of electromagnetic radiation passing through a substance is absorbed. In this case, we're saying these certain frequencies of electromagnetic radiation are emitted. They are emitted due to an atom making a transition. So we're having now the atom that is moving from higher energy state to a lower energy state. Remember, when electrons, when they gain energy, they move from lower energy level to higher energy level. That we refer to as excited state. But for electrons to move down, they have to emit or release the same amount of energy. So we're saying this one, which is called atomic emission spectrum, is formed when certain frequencies of electromagnetic radiation are emitted due to an atom. An atom is moving from a higher energy level to a lower energy level. And say for it to move from lower energy, remember what made it to be at a higher energy level. It means it has gained or it has absorbed energy, because when atoms absorb energy, when electrons get energy, they become excited, then they move to higher energy level. Then we're saying when the electron is at a higher energy level, when it loses that energy that it had, then it is emission. Hence we are saying is when the atom is moving from higher energy level to a lower energy level state. So always remember with atomic emission spectra, all of them were saying certain frequencies of electromagnetic radiation. The difference is that here on the emission, these certain frequencies of electromagnetic radiation are emitted due to an atom making a transition, moving from higher energy level to lower energy level. So I hope you got that, and you see now the difference between atomic absorption spectrum and atomic emission spectrum. For example, we are saying the atoms in hot gas, definitely when we have hot gas, it will emit light at characteristic frequencies. The spectrum absorbed is a line spectrum with only a few colored lines. So we'll have a line spectrum with only few colored lines of frequencies unique to the type of atom that is producing the emission line. So I talked to that. I hope you are happy with that, and you will see that you understand the difference now between atomic absorption spectrum to say, okay, certain frequencies of electromagnetic radiation that you say in both definition. What differs is that those certain frequencies of electromagnetic radiation passing through a substance is absorbed for absorption. But for emission, these certain frequencies of electromagnetic radiation are emitted. They are emitted due to an atom making a transition from. So don't just say certain frequencies of electromagnetic radiation are emitted. You must be able to tell us why they are emitted. They are emitted because the atom is moving or is transitioning from higher energy level to lower energy state. Thank you very much in terms of that. I hope we are together, and I'm happy that I've laid a foundation, because with these definitions, there are 5 definitions which I've emphasized. Photoelectric effect, the first one. Threshold frequency, the second one. Work function, the third one. The fourth one being atomic absorption spectrum. The fifth one being atomic emission spectrum. I hope you are happy with this, and you will always remember them. And when you get them in the exam or in any other assessment, you will be able to answer the questions. Now, let's look at what you are bringing here to grade 12. You are not coming empty. In grade 10, I always emphasize to yourself to say we are doing what is called National Senior Certificate, which is a 3-year course. You have started NSC, your NSC, you have started in grade 10, year number 1, when you started FET. In grade 11, you were year number 2. Grade 12, you are in the final year of the National Senior Certificate. That's why end of this year, you will write your exams and you'll be expecting to get your National Senior Certificate. Now, in grade 10, your first year of FET or your first year of your NSC, you did what is called electromagnetic spectrum. Electromagnetic spectrum, you have done that. So we're going to look at that electromagnetic spectrum. You will remember. I usually like to refer to this as Rami Vuksch, so that you remember. You see, I will always be giving you this so that you how to remember things that will help you to remember all these. Remember, you talked about the radio waves, microwaves, your infrared, your violet, your UV, ultraviolet, your X-ray, and your gamma rays. So all those are electromagnetic, orange, yellow, as you go to the right like that. So all these colors, we are saying they fall under visible. But all in all, when you talk about electromagnetic spectrum, we're talking about your radio waves, your microwaves. Hence, we are saying we apply this at home. We use the radio, we use the TV where they are using the radio waves. We use the microwave there. So all these are important, and you have heard about X-rays and then the gamma rays as well. Then we'll be looking at all of them, and then you have done this in grade 10. And we're saying you must know the nature of electromagnetic radiation, and you must be able to list them. The electromagnetic radiation, to list them, like I've done it easier for you, Rami Fuchs, to remember how they are ordered there. And then you must be able to know their penetrating ability. You have done that, penetrating ability in relation to energy and frequency. Yes, and then you must be able to know that. And then what we said, we're talking about the particle nature of light. You remember, we said light has dual nature. It can exist as a wave, it can exist as a particle. So in this section, we're focusing on the particle nature of light. And then the concept of a photon. I told you about this one, which we refer to as a packet of energy. You can see now I'm giving another definition to say this is a packet of energy, which we say is a quantum. It's a quantum. It's a quanta for plural. So this photon is energy of a photon, which is given by E equals to HF. And then we know that frequency is equals to C over lambda. So sometimes you always check whether you are given frequency or you are given wavelength. If you are given wavelength, you will use the HC over lambda as your formula to calculate energy of a photon. If you are given frequency, you'll just use E equals to HF. Hence, it's always important that we always emphasize to say, always do your data collection. What are we given, so that you know how to solve the problem. That is the first problem solving skills for physical sciences, to say you must always do data collection. Now, this is what we have done in grade 10. Remember, when we were doing the waves, you had the formula V equals to F lambda. But remember, now we're talking about the speed of light, not the speed of sound. I think you have seen that V equals to F lambda when we were doing Doppler effect. But now we will be talking about C equals to F lambda, which is now the speed of light equals to. So always let's remember that. And remember, C is a constant, and it's given is 3 times 10 to the power of 8 meters per second squared. Meters per second. So, and then we are saying this C, which is your constant. You can say 3 times 10 to the power of 8. Sometimes you say 300 million meters per second. It's still referring to the same value of C, and you will be able to utilize that. Remember this one, you dealt with it when we were dealing with the speed of sound, when we're dealing with the Doppler effect and all that. Now we're talking about C for this light that we're talking about. So that's the main thing that you must see. But this, in terms of formulas, you were doing them like this in grade 10. You even know how to calculate your period, which is 1 over F, like that. So all this is your prior knowledge. We're saying we appreciate this, and then you have done this. So you can go to a grade 10 textbook or a grade 10 classwork book and check and remind yourself of all this knowledge, because we're just building on that house that you have started in grade 10. Now, let's do a baseline activity. So our baseline is still based in grade 10. So you can appreciate the importance of this prior knowledge. To say, here this one is saying red light of frequency F and wavelength shines on an object. The red light is then replaced by a light of higher energy. Remember, I was referring to those colors, your white beef. Remember, we are saying that when the wavelength, when the red light is having the highest wavelength, when it has the highest wavelength, it means it has the lowest energy. So it's important that you have that information to say what is the relationship between frequency and wavelength. So if red light have the highest wavelength of all these 7 colors that I'm talking about here, it means that this red light will now have the lowest frequency, because these two are inversely proportional. Frequency is inversely proportional to wavelength. And by so doing, you know that from the formula E equals to HF, the relationship between E and energy of a photon and frequency is that they are directly proportional. So if you have a lower frequency, it means you have a lower energy. So you will see that for red color is the one that is having the lowest energy. It is the one with the lowest energy. As you move to the right, the energy is increasing. Why is that? Because red color has the lowest frequency, and then which means it has the highest wavelength. So they are saying now the red light is then replaced. This one is replaced. So you can replace it with any color of your choice here. But immediately when you move that way, it means now the wavelength is decreasing while the frequency is increasing. And by so doing, immediately when you move that side, the frequency and the wavelength of the light shining on the object, how will it compare? So I think I've answered your question. Number A is saying when we replace red, let's say with any color, there will be greater frequency. Yes, frequency increases. So this is correct. But the relationship between frequency and wavelength is that when frequency increases, the wavelength decreases. It does not remain the same. That makes that one wrong. Now let's look at number B then. It's saying the frequency will be less than, wrong. The wavelength will be greater than, wrong. And then greater than, we've agreed that greater than for frequency, because we are moving to lights of lower frequency, of lower wavelength but higher frequency. So definitely the wavelength will decrease, and then the frequency will increase, and C becomes our answer. So you are able to answer that question, and this is the same thing that we will be applying now in grade 12 to answer the questions. Now if we continue with our baseline, we are given the types of electromagnetic radiation that are arranged according to the frequency in the table below. So we are given, that's a question. We are given your Rami Fuchs, as I told you, your radio waves, microwaves, infrared, your visible light, ultraviolet, X-rays, and gamma rays. We are given their frequencies. You can see that those ranges of frequency there. For radio waves, we have 10 to the power of 5 to 10 to the power of 10, microwaves 10 to the power of 10 to 10 to the power of 11. So you can see that as we move from radio waves, remember I said Rami, books, don't forget that one. I'm always saying it because I want you to remember and know that from radio has the lowest frequency. The radio waves has the lowest frequency. The gamma rays has the highest frequency. So don't confuse the R for rate. Remember with the rate, we said it has the lowest frequency because it has the highest wavelength. So you got not confuse that. When we're talking about this one, we're saying now your radio waves are those ones, and then it's the lowest frequency. Your gamma rays have the highest, as indicated there. So you can see from the table. Let's go now to questions. How are these electromagnetic waves generated? So we're saying they are generated by the accelerating charges. Those accelerating charges, they are the ones that generate these electromagnetic waves. And then 2.2, what type of electromagnetic radiation has the highest energy? Already you are coming here to say frequency and energy are directly proportional. From the formula, E equals to HF, which means the one with the highest frequency, it has the highest energy. Hence, we are saying gamma rays will be having the highest energy because they have the highest frequency. Now, 2.3, explain the answer. I think I've done that already to say that why this is so. So we're saying as you move from radio waves to gamma rays, there is increase in frequency. So, and when frequency increases, energy increases. So energy is directly proportional to frequency. So that will be your answer to say gamma rays have the highest frequency, and if they have that, frequency is energy is directly proportional to frequency, and then you are able to get your 2 marks there, and then you are moving. So important. All this we have done in grade 10, and we are going to apply all this knowledge now as we come to the end of our baseline activity. We are still on the same question, statement. Now they are saying now a certain type of electromagnetic radiation has a wavelength. Remember, we are given the wavelength. When you are given the wavelength, you will remember I told you about the C equals to F lambda. You'll remember this formula to say, okay, C is the speed of light, which we said is 300 million meters per second, or 3 times 10 to the power of 8 meters per second, and you are given the wavelength. So you are able to determine your frequency. So you are able to determine, because you will write, you will substitute the C, you will substitute the wavelength that is given, and then you are able to get your frequency. When you get your frequency, you will be able to answer the question that you will be asked. So it's important that you have that in mind. The question was, identify the type of electromagnetic radiation by performing a calculation, which means when you get your frequency there, you must be able to come to the table and identify which of these has that frequency. And then if you do that calculation, you will have seen that you will do your 3 times 10 to the power of 6 as your speed of light, and then you will do that. You substitute as well your wavelength there, and then you are able to get your answer, and then you are able to come back there and say and say that you got your ultraviolet as the light, which is this one, which is the 10 to the power of 15. So you see that is UV, that is the answer. Then you are able to get your answer. So it's important that you are able to always remember that one. Now, state one application of the type of radiation identified. Ultraviolet, where do we use the ultraviolet? You will see that when you're dealing with your medical equipment, you will use UV for sterilization, or they use it for in the astronomy. So it's important that you know, and you say ETC. So we're saying you must know this application as many as you can, because as a science learner, you got to have that knowledge. Now, let's come to grade 12. So we have invested a lot on the prior knowledge to say, what do you know as of now? Now we are taking that information, we're bringing it now to grade 12 to say, now in grade 12 we talk about the concept of photoelectric effect. Remember, we said here we're going to eject, the process whereby electrons from the metal surface are ejected when light of certain frequency is shown onto it. So we got to know the definition of photoelectric effect, as I've emphasized, threshold frequency, which you said it was the minimum frequency needed by the electron in order to be ejected from the metal surface, the work function being the minimum energy that is required. And we talked about atomic absorption spectrum and atomic emission spectrum. And then you must be able to know the effect of intensity. I said intensity, we're talking about the brightness. If the color becomes much brighter, what does it mean? So that's what we're going to focus on in grade 12. And then we're going to focus on the importance or significance of photoelectric effect. Already you have seen we're going to talk where do we do the application of this photoelectric effect. The use of the equation, we call it photoelectric effect equation, which is your E equals to W naught, which is work function, plus EK max. Please always indicate that is the maximum EK. And then remember, if the formula is E equals to the work function, energy of a photon is equals to the work function plus EK max. We are saying if it's EK max, we can even expand it and say work function plus half mv squared. But don't forget, it's a maximum speed of that electron. Hey, you are asking yourself, where will I get the m from? M is a constant, is the mass that is given in the data sheet. You just have to go and look for the mass of an electron, which remains constant, and then you are able to do the substitution. So we are hoping that this is what you are going to do, as we will be doing questions, and then it will help us as we move forward. Now, definitions, I've talked about them: photoelectric effect, threshold frequency, work function. We said all those definitions you must know. In addition, number 4 and number 5, atomic absorption spectra, atomic emission spectra. So you got to know all those 5 definitions. Now, let's look at the electromagnetic spectra. Remember, we said Rami Fuchs. I'm always saying that so that remember. You know, when you know, and then you won't forget, because you'll be knowing to say we have those seven electromagnetic radiation is those 7, and then this is the spectrum. Is the range. When we say electromagnetic spectrum, we're saying the range of all frequencies of electromagnetic radiation. So these are electromagnetic radiation. We are referring to this as a spectrum because we are having a range of all of them to say this one, for example, the wavelength for radio waves, we are saying is 10 to the power of 3, microwave 10 to the power of -2, 10 to the power of -5 for infrared, visible light, which is a half times 10 to the power of -6, UV, X-ray, and gamma ray. So you can see as we move from radio wave to the gamma ray, the wavelength decreases, and as the wavelength decreases, the frequency increases. So you can see the frequency is increasing from 10 to the power of 4 for radio waves to 10 to the power of 20 for gamma rays. So you can see that if you're exposed to those gamma rays, definitely it's not good for you, because it's the energy there is too much energy that we're having there. So you will be able to see that will be cancer forming if you're exposed to that type of light. Now let's focus. Remember, from the previous slide, remember we had this, which you said it is the visible light. Hence, you see the eye there to show that you can see them with your naked eyes. But you can see with your radio waves. It includes your phones, your radios, all that, your microwave that you are using at home, your infrared, your remote control there, your UV, and then hence we are saying you see the energy from the sun. We're saying that don't expose yourself from that UV, because it can be problem as well. And then your X-ray, and then your gamma ray. So you can see that all this. But now we're going to focus on this one, which is the visible light. The visible light, hence we are having this light that follows. To say the visible light spectrum, it is like that. And then you can see that for the visible one, we have a roic beef there, then with the red, orange, yellow in that order. So you are able to see that these are the wavelength in nanometers, and then you are able to see that as you are moving, they will be changing from 725 to 450 for violet. You can see that the wavelength is decreasing, and you know that as the wavelength decreases, the energy increases. So you can be able to see that these ones will have with the lowest wavelength, they will have the highest energy. Hence, we have them like that. So important as we move. Now, I thought it will be very important that we do the demonstration to show you what happens when we expose the metal surface. Now, remember, I want you to have this understanding. The understanding is that we are having the work function. We're having two energies that we must compare at all times, which is the energy of light, energy of a photon. Energy of a photon, which is HF, we must always compare it to the work function, which is the minimum energy. It's like, you see that the metal is saying, for me to release my electrons, I need this much. Each electron needs that energy. Hence, we are saying this light is providing packets of energy, a quantum of that particular energy, which is HF, which means now every dot you see there is a quantum, and one photon for one electron. That is what you got to have the understanding there, to say, okay, we're having this now photons, which are packet of energies that now are targeting the metal surface. Remember, metal surface has electrons, but these electrons, they have work function, they have expectation. They're saying the minimum that you must give me energy, that you must provide for me to release the electrons is this much. So we'll always check to say, okay, if this energy that is being provided is less than the work function, definitely the electrons will gain the energy. Hence, there will be vibration. There might be vibration as the electrons are moving from lower energy level to higher energy level. But electrons won't be ejected from the metal surface. But immediately, when the energy of a photon, the tricky one, energy of the photon is W0. When they are equal, the electron will be removed. But when the two are equal, electrons will be removed, but EK will be equals to 0, which means they will be removed, but they will still be localized. They won't be able to move away. They won't be able to move away, but they will be removal when they are equal. But when it's greater, the energy of the photon, when it's greater than the expected one, which is the minimum energy required, which is the work function, we're saying there will be removal of electrons, and the other energy will be converted to maximum kinetic energy. Hence, we give the formula like that. So all the other energy will be converted to kinetic energy. Now, if I can show you now this demonstration, you can see. So we're having our UV light now that is exposed now to, that is exposing, and then when this exposed there, you can be able to see what happens now. What happens when the light hits our cathode? Here we're having our cathode. It's a nice experiment. We're having our cathode, which is negatively charged. We're having our anode on the other side. So you can see we have negative this side of the cathode. It is the cathode, and then we're on the other side we'll have a positive, and then you are able to see that one. Now if I can go back to it, then you are able to see the experiment that is being done there. So you got to see that we're having the light, which is bringing now the photons, and when the photons are busy are bombarding the metal surface, electrons are ejected. That's why we're calling it photoelectric effect. And we're saying we can move around in terms of colors. We can move around. Remember, we can move around from red. Yes, you will see that red as being now having the lowest energy because it has the highest frequency. Red, most of the time, it won't be able to remove or to eject the electrons when you are dealing with red, but it can to a minimum. For example, when you are dealing with metals like cesium, you will see that it's able, the brightest of the red color will be able to remove, but all generally the energy of red color is the lowest, and then hence it becomes difficult for it to eject electrons. And what is important is that as the electrons are ejected, we'll talk about current. We'll talk about current, which is now your I equals to Q over T. So you can be able to see that there is current, because hence we can measure current there. When electrons are flowing, there will definitely be current, and then you are able to have that. So I hope that helps you to be able to have an understanding to say, as the electrons are flowing, we can talk about the current now, because now there is movement of electrons. Where is this concept coming from? I felt it's important that we must take through this journey to say, where is this one coming from? We have our Albert Einstein, who did this photoelectric effect. Now we are saying, when a metal surface are exposed to electromagnetic radiation with sufficient energy, they absorb the photons of energy and emit electrons, which is what we have been talking about. This process is called photoelectric effect. How did it all start? It started with Henry Hertz, was the first to discover this phenomenon in 1887 when he was investigating radio waves. In 1901, you can see now we are moving Max Planck, hence we are using the Planck as constant, show that energy is quantized. The formula E equals to HF. Hence H, we refer to it as Planck's constant, because it is Max Planck in 1901 who was able to show that energy is quantized. And then Albert Einstein, he came and explained it. He explained it in 1905. Then he was able to take a metal, for example, here we're given a sodium metal. Light was shining on a clean sodium metal in a vacuum, and electrons were ejected. So we're able to see that, okay, what happens when the light, when the electron, remember we are referring to electromagnetic radiation and light. We are changing. Sometimes I will refer to light, sometimes I will refer to electromagnetic radiation, being referring to the same thing. When the metal surface is exposed to the electromagnetic radiation or to the light, what will happen is that the electrons will absorb energy, and if that energy is equal to the threshold frequency or greater than a threshold frequency, electrons will be ejected or removed from the metal surface, and then we'll say photoelectric effect took place. So very much important. Now we are saying this electromagnetic radiation consists of small particles or packets of energy. We talked about them, called photons. I said it's quantum of photons. Each photon carries energy proportional to its frequency. So the energy of a photon is directly proportional to the frequency. You have seen when you did the activity. Electrons have free electrons. Remember, we refer to them as the valence electrons. Metals, valence electrons, and then you will see group 1 metals where sodium is. They'll have that 1 valence electron. Group 2 elements will have that 2. Group 13, where we have aluminium, they'll have 3 valence electrons and all that. So we take advantage of that. Hence, when we bring light, we know that light will be absorbed by the electrons, and when they absorb the energy, they will become excited. They'll move from lower energy level to higher energy level. And we're saying if the energy is equals or greater than work function, the electrons will be removed from the metal surface. So hence we are explaining that here to say the other energy will be converted to kinetic energy. So I think I've talked about that. And then we're saying now here, if the energy gain is sufficient, the electron will escape from the metal surface. This process is called photoelectric effect. And part of this energy gained by the electron is used to release the electron from the surface to overcome the forces of attraction between the electrons and the metal, and the rest as kinetic energy. I talked about that to say the other one is to go and dislodge the electron from the metal surface, to remove the electron from the metal surface. When it is released from the metal surface, the rest of energy is converted to kinetic energy. So that's what we are saying, and we are saying that the magnitude of this energy is a few electron volts. It's a few electron volts, and then the frequency that corresponds to this energy is the threshold frequency. Now, we talked about the work function and threshold frequency, the relationship there being W naught, which is the work function, is equals to HF0, H being Planck's constant, and F0 being your threshold frequency. So there will be times when you are not given the work function, you are given threshold frequency, so you are able to calculate work function before you use the photoelectric effect equation. Electrons are only emitted if the frequency of radiation is greater than the threshold frequency. So there will be time when you will be comparing the frequency and the threshold frequency, the frequency of light and the threshold frequency, because you know that the energy is there. Remember, when it's energy, you simply say E equals to HF. We are using that F, and then when it's work function, you will say work function is equals to HF0. So you can see that work function is directly proportional to F0, and energy is directly proportional to frequency. So that is important as well. Now let's move, and then the photoelectric equation already, you can expand it to E, from E equals E, which is HF, work function, and then half mv squared. It must be maximum speed there, and then you are able to do the calculation. So the question is, why is this photoelectric effect so important? So we're saying it is important because it helps us to explain the particle nature of light, and it is the basis for quantum theory, and it is used in photocells. Example, in solar calculators. I think maybe as a science learners, you have seen the solar calculators, and then the alarm systems that you are having, the automatic doors that you come across when you go to the shops, to your mall, wherever you are going, where there are automatic doors. Those automatic doors that we refer to, we are saying now it is the application of this photoelectric. So you can see photoelectric effect is very much important that you know about it. And then in terms of the data sheet, you saw I've indicated that, remember, we are not using the V equals F lambda that we use in the Doppler effect. We are using C equals to F lambda. So it's important that you always remember that now we are moving with that one equation, which is important. Now, and then as well, you know the other equation, Doppler effect equation is like that. You can expand it depending on the question that is asked. So please have that information. The data sheet is there so that you are always able to go back and refer. Don't forget E equals to HF. If you are given wavelength, you will use E equals to HC over lambda, and then still you are able to do that. And I've talked to this one to say electron can only absorb one photon. I told you the relationship there. One packet of energy for one electron. So hence, when we talk about increasing the intensity, it means we are increasing the number of packets, the number of photons per unit time. So it's important that you have that. We said the photon is equals to HF. I've talked to this one already to say when the energy of a photon is less than what is required, which is the work function, electrons will not be ejected. But when they are equal, photons absorbed and photoelectron ejected, but EK will be 0. We talked to all of this. And then when it's greater, we're saying the electron will be removed. After the electron is removed, excess energy will be converted to kinetic energy of a photoelectron. You see the electron that has now absorbed the energy. We are referring to it as a photoelectron. So important. Now, I thought this will be important. When the energy of the photon, you can see the light there, is beaming below threshold. So you can see that there are no electrons that are moving, but it doesn't mean that the electrons are not absorbing the energy. They are absorbing the energy, but the energy is less than the work function. So in this case, we can say the frequency of light is less than the threshold frequency. We can say that the energy of the photon, the energy of light, is less than the work function, hence no photoelectric effect. That is the demonstration. I hope it helps you. And again, when it is greater than the work function, you can see what happens now. You can see that when we bombard now the electrons with the photons beam above threshold frequency, you can see that they will absorb the energy and they will be ejected, and this is what we call photoelectric effect. So I hope this they are able to show you that this is what is happening, and it always depends on the relationship: how much energy of a photon, how much work function, how much do you want, how much do I have. Then you are able to look at the two. If it's less, you know, no photoelectric. If they are equal, there is removal but no EK. If it's greater than, there will be removal and movement, which is EK max. I hope you got that. As we go towards now activities and calculations. Now I've talked to these formulas, I've explained them, and I'm hoping that now you are ready and you can be able to utilize all this. Now, those are for calculations. We talked about the brightness of light, comparing a brighter light to a dimmer light. What happens whenever a brighter light and a dimmer light with the same frequency? Brighter light contains more photons. I want you to have understanding, to say we have more packets of energy with the, so when we increase intensity, it means we are increasing the number of photons per unit time. It means now we'll have more photons and more photoelectrons ejected every second. What does that mean? Always we are comparing the energy of the photon and the work function. If the energy of the photon is less than work function, even if you increase the brightness of light, still you are just increasing the number of these photons, but they carry the same energy, so they still won't be able to eject the electrons. But now, if the energy of a photon is greater than work function, when you increase the brightness, or when you increase the intensity, it means that you will have more photoelectrons that will be ejected per second. So it's important that you have that understanding, to say for same frequency, photons have the same energy and each photoelectron has the same EK. So for same energy, you won't have different EK. They will all have the same speed. They will all have the same maximum kinetic energy. Now, you will be coming across a lot of graphs. So it's important that you know that light of different frequencies is shown onto a metal, and the kinetic energy of the photoelectrons is measured for each frequency, and then EK is plotted against frequency. So you can see we have the y-axis there as your EK. You have the x-axis there as your frequency F. So you can be able to see that we're having those two. And then this is a straight line graph, and it intercepts here where EK equals to 0. And when EK equals to 0, we're talking about threshold frequency. It means now the threshold frequency, you will always get it where our graph cuts the x-axis. I hope we are together on that one. And then we are saying the gradient of this graph is h. So the gradient of this graph is Planck's constant. So it means when you calculate the graph, the gradient, remember the gradient is change in y. over change in x. In this case, change in ek over change in frequency. That will be our gradient, and we are saying that is equals to h, and h is Planck constant, and then it means now the gradient of this graph. Always when you're given that graph, you must know that the gradient will be our Planck's electrons. And we have emphasized that no electrons will be emitted when the frequency of light is less than the threshold frequency. So I hope it will help you, as we'll be doing questions now that include graphs as well. Intensity, I talked about it to say the number of electrons emitted per unit time is proportional to the intensity. So when you increase intensity, you will increase the number of electrons removed per unit time. Effect of frequency, the maximum kinetic energy of photoelectron is linearly proportional to the frequency of the incident radiation. So you got to always check, when you increase frequency, we're increasing kinetic energy. Please don't be confused here. We are saying that what will always increase? What will increase? Somebody was saying when we increase the brightness, which is the intensity, when brightness increases, the current will increase as well. And then when you increase your frequency, your kinetic energy will increase. So it's biggie, figgy, you are able to remember that. And then if it helps, then you always check that, okay, the current will increase when you increase the brightness, which is the intensity of light. It means we're increasing the number of photons per unit time. And then when we increase the frequency, we're increasing the kinetic energy as well. Then you are able now to do that and be able to move. Now, here is an activity. I think you are happy. You have been waiting for activities so that you can do exam type questions. Remember, all these are exam type questions because we are preparing you for the exams. Remember, we are saying in physical sciences, step number 1 is to read with understanding. You read with understanding. With your highlighter, you are able to highlight important information, and after that, you are going to do what we refer to as data collection. After you've done data collection, you are going to look for the formula. When you have the formula, you are going to substitute. When you substitute, you find the answer with the correct unit. We always are saying that is our everyday song. Now, let's look at this one, our very first activity 1. It says, the work function of potassium is, so you know potassium is a metal. So we have two things. We have the metal, which in this case is potassium. It has, the metal has work function, which is W0. It is given there, 3.52 times 10 to the power of minus 19. An electromagnetic radiation strike on the surface of this metal produces the photoelectric. When say produces the photoelectric, means electrons are ejected, electrons are removed. The maximum kinetic energy of the electrons ejected is that one. So we have W0, we have maximum EK, which is this, and we know that E equals to that. So this were given, maximum EK were given. Nice. So you can see already by doing data collection, it helps you to understand what type of questions you might be asked. Now let's go. It says, define, sorry for that. It said define, it said define work function as our first question. Remember previous exam. Hence I have emphasized that those 5 definitions, always know them. Photoelectric effect, work function, threshold frequency, atomic absorption spectra, atomic emission spectra. This one is your song. As long as you are talking about question 10, the last question of your question paper, you will be dealing with those 5 definitions. In this case, they say define work function, and you know work function we said is the minimum energy that is required by the electron in order for it to be ejected from the metal surface. Minimum energy needed to eject an electron from a metal surface is called work function. And then define photoelectric effect. It's good when you find in one question paper you have 2 definitions, you must be happy because already you are collecting 4 marks there, and then that is nice. And then you are able to say it's the process whereby electrons are ejected from a metal surface when light of suitable frequency is incident on that surface. Now let's move to 1.3, which is now a calculation. Activity 1.3 is based on the calculation. Remember, we still have that given information that we are having the work function, we are having EK. So you know E equals to work function plus EK. EK max was given, W0 was given. Then let's see the kind of question. Calculate the frequency. Already you knew that because this one and this one are given, definitely the question when it comes, it will be based on this one. And then they are saying, no, if we say calculate energy, we'll just add the two. So they didn't ask you that question, but you are asked now to calculate the frequency, and you know that E equals to HF. Already you know that E equals to HF, and then you're having that plus EK max. So you're able to see that, this one, I'm going to get this one. You just have to divide by Planck constant both sides. After substitution, remember, we are always saying, please substitute before you do any manipulation of the equation. We don't always encourage you to manipulate and make frequency subject of the formula. You make mistakes. Just substitute on the formula like that, and then you are able, after that, then you are able to divide both sides by Planck's constant, and then you are able to get your answer. And without any wasting of time, you will have done that and said E equals to work function plus EK. As we said, you said HF there, and then you just substitute your Planck's constant, which is 6,63 times 10 to the power of minus 34, and then your work function was given as 3,52 times 10 to the power of minus 19. Your EK max was given as 4,2 times 10 to the power of minus 19 joules. So you just substitute all of them like that, and then you are able now to get your answer, which is frequency, by dividing both sides by 6,63 times 10 to the power of minus 34. So just imagine having done that, you got your answer and you are ready to go. So it's very much important that you always start with the photoelectric equation in mind. That is what at all times you are preoccupied with, that when you are dealing with calculations, to say this is where I'm going, what is that which I'm given, and then you are saying I'm given EK max and I'm given the threshold, the work function, and because I'm given those two, they are looking for frequency. Definitely I will substitute the Planck's constant and divide both sides by the Planck's constant and be able to get my answer with no problem. Now, the wavelength of the incident radiation. Now they are saying, now calculate the wavelength of the incident radiation. So you know the relationship already. When you know frequency, you know the relationship now. The C equals F lambda. That relationship definitely is going to help you, because now we're looking for the lambda, which is your wavelength, your wavelength, and you know you said C equals to F lambda. You were able to calculate frequency here as 1,6 times 10 to the power of 15. Then it becomes easier for you now to say this is what I'm going to do, and then with no any waste of time, you are able to use C equals to F lambda, and then you are able to calculate your lambda, which is your wavelength. What I want to emphasize is the issue of the SI unit. Remember, if the SI unit is wrong, we won't mark the final answer. So always know that the wavelength is in meters, frequency is in hertz, energy is in joules. Can be kinetic energy, will be in joules. Energy of a photon will be in joules. Your work function is in energy, will be in joules. I know you will have seen somewhere, maybe you came across electron volts, but in this case, in terms of our calculation, we're using SI unit for energy as joules. SI unit for frequency, always it is hertz. SI units of wavelength, it is meters. And ensure that you do that, because some of the questions you'll be given wavelength in millimeters, in centimeters. So the expectation is that you must be able to convert. And those small technicalities are the ones that sometimes makes learners not to get correct answers. I hope that information helps you as we go now to activity 1.4. Remember, we talked about intensity. So this question is based on the intensity, to say the intensity of the incident radiation on a metal plate is increased. So we're increasing the intensity. Remember, they can ask you when intensity is decreased. We don't have to be always cramming that we got to talk about brighter. Remember, we said brighter light. You are increasing the intensity. And don't forget, when we increase intensity, what does it mean? We're increasing the number of photons per unit time. So you got to know that it's number of photons, but all these photons, they carry the same amount of energy. I want to emphasize this because that's where, when you have that information, definitely it's going to work for you and you will be able to answer many questions. So I think the intensity of the intensity of the incident radiation on the metal plate is increased while maintaining a constant frequency. So these photons, these many photons that are being brought in, they have the same. So EK cannot be affected if the intensity is increased because they have constant frequency, which means frequency is remaining the same, and frequency is directly proportional to energy. If frequency remains the same, it will mean that the energy remains the same. Now the question is, state and explain what effect this change has on the following. State and explain what this effect has on the following. I'll just pause when I show you the question. I'll just pause for a minute or so, and so that you are able to answer the question. Then we'll talk about the answer. Now the issue here, they are saying we've increased the intensity. Now they are saying what, state and explain what effect when we increase intensity, what is the effect on kinetic energy? Increase intensity, will kinetic energy increase? Will kinetic energy decrease? Will kinetic energy remain the same? And you got to give a reason to explain why it is like that. Definitely, I can say you are thinking to say, okay, when you increase intensity, the frequency remain the same, and this kinetic energy will be affected. Hence, I said to you, Fiki there, so that you remember that frequency increase will increase kinetic energy. Kinetic energy will increase when frequency increases. But when the frequency remains constant, it means kinetic energy will as well remain the same. So definitely, as you answer that question, you will be able to say kinetic energy will remain the same. Why will kinetic energy remain the same? Because kinetic energy depends on energy of individual photons. It depends on frequency. It does not depend on how many photons. Intensity means how many photons. So when say we're increasing photons, we're increasing intensity, we're increasing the number of photons that are there. So in this case, we've increased the number of photons, but they carry the same amount of energy. Hence, we are saying now, because frequency remains the same, it means energy will remain the same. And then, hence, if that is the case, kinetic energy is the same. Now, let's move. The next one is saying, what will happen to the number of photoelectrons? Oh, very interesting. The number of photoelectrons, remember we said big there, that okay, as you increase the brightness or the intensity increases, we are saying now the current will increase, which means the number of photoelectrons per unit time will increase. The number of photoelectrons ejected or emitted will increase, because when we increase intensity, we increase the current, we increase the number of photoelectrons that will be emitted. Definitely, you are able to respond and say the number of photoelectrons emitted will increase, because we are saying the number of electrons emitted per unit time is proportional to the intensity of the incident light. So when we increase the incident light, we are increasing the number of photoelectrons emitted per unit time. So must we always refer to them as photoelectrons? You can refer to them as electrons. You can refer to them as electrons. We say photoelectrons, it's a plus. So we appreciate that. Now we are going to the question that is based on the graph. So in a photoelectric investigation, light of different frequencies was radiated on each of the two metals. So we're having two metals, it's metal A and metal B. So we're having metal A and metal B. The graph of the maximum kinetic energy of the ejected electrons from metal A and the frequency of the incident photon is shown below. So you can see, nice graph. I think by now you know what does it mean here where the graph is doing all that. Let me leave you to it so that you are able to answer. I don't want to take you to where you are supposed to go. Now in the statement, they are saying point X on the graph represent unknown maximum kinetic energy. So it's a maximum kinetic energy. It's a maximum kinetic energy which is unknown. Now they said write down the numerical value of the gradient of the graph. The gradient of the graph. So we talked about this one to say the EK versus frequency graph, the gradient, it is Planck's constant. So they are simply saying write Planck's constant, and then definitely you will be able to say 6,63 times 10 to the power of minus 34 joules as Planck's constant. Now I want you to do this one. Define the term work function. You are able to define work function. Remember, we said it's the minimum energy required to eject electrons from the metal surface. So you're able to say like that, and you get your 2 marks there. So it's important that you know these definitions. They will definitely help you. Now, this one is saying calculate the work function of metal A. Calculate the work function of metal A. So remember, you must be able to interpret the graph in order for you to do that. And then you see that when EK is 0, we have F0, which is the threshold frequency. Now, the mistake that learners make is that they will think that the threshold frequency, it is 5 here. For metal A, they will think that the threshold frequency is 5 here. And then that becomes a what? A problem, because definitely it won't be 5 because it's times 10 to the power of 14 hertz. So please always refer to that, because once you write 5, you will go out of the exam room, you will tell people the exam was easy, and then only to find that you didn't write the correct frequency, because it is 5 times 10 to the power of 14 hertz. So when you are doing that, be able as well to look into that, and it will definitely help you. You know, most work function, we're talking about W0, which we said is equals to HF0. HF0 said is Planck constant, which we said is 6,63 times 10 to the power of minus 34, or F0, you got it. So definitely you are able to do your calculation by substituting your 5 times 10 to the power of 14. The 14 is the power there, and then times 10 to the power of minus 34. You are able to calculate, multiply the 2, and you get 3,32 times 10 to the power of minus 19 joules. Remember, we said it is measured in joules. It is measured in joules. And then calculate the value of X, this one. So I'm going to give you this one about 5 minutes that you calculate the value of X. I'm giving you an opportunity. This one, you do it on your own. You think, what am I supposed to do to get the value of X? So see you in 5 minutes time when you will have been done with that calculation. You see, I gave you a bonus 1 minute because it's 4 marks at least. By one minute for every mark, you can be able to finish. In 5 minutes, you will be done. So see you in 5 minutes. Calculate the value of X shown on the graph. Thank you. Welcome back. I hope you were able to calculate the value of x shown on the graph. So you already know that your Planck's constant is the gradient. Gradient we give it as change in y over change in x, which in this case your gradient you said is h, which is Planck's constant, and the change in y is change in ek, and then your change in x is your change in frequency. So you're able to see that is the way to go, because you want to find the k there. You want to find the k, and then you are given all that information. So I hope you went along those lines. You were able to go with your gradient, which is your h, which is your 6,63 times 10 to the power of minus 30 minus 34. And then on the x, you have x minus 0, change in y is x minus 0. You are able to write that. And then your change in frequency, we can see that is your 12,54 times 10 to the power of 54 minus the 5 times 10 to the power of 14. Please don't forget times 10 to the power of 14. Hence I was emphasizing it. And you are able to get 1 mark for writing the correct formula of your gradient. And then you get another mark for substituting your Planck's constant, your h, which is 6,63 times 10 to the power of minus 34. And then we're saying now changing y is x minus 0. You're able to write that. Changing x, you're able to write that. Then you get another mark. So already you have 3 marks. You are only left with 1 mark of doing the maths. Please practice these questions, more especially because we are talking about powers of minus 34 to the power of 14. Have your scientific calculator, do calculation, get used to a calculator. And we are always saying, don't change the calculator that you are using. If you are used to a particular calculator, continue to utilize that calculator, because the expectation is that in the exam you will be used to that calculator and you won't have problem. Just imagine going to exam with a new calculator. It will be a problem because you won't know how to operate it, and you will be able to misuse a lot of time. So it's important that you use a calculator, you get used to that calculator. And when you cross multiply there, you are able to get your x. I hope you got it, as 5 times 10 to the power of minus 19 joules. So now that is your answer that you got, and then we're able to give you your mark there, which is your final answer. Or else another learner can say, no, I want to use the photoelectric effect equation. Still, it will help you to determine your x. In this case, you are having your h, which is your Planck's constant, multiplied by the frequency, which is 12,54 times 10 to the power of 14, and then that is that part of hf, which is E equals hf. You're able to substitute that, and then your work function, which was 3,32 times 10 to the power of minus 19, and then you are able to substitute that, and then you're going to calculate your ek max. So as well, if you utilize this equation, you will still be able to get your 4 marks, which is x equals to 5 times 10 to the power of minus 19 joules. But I will always encourage that when you're given graphs like this, just work with your gradient. It makes it easier. But however, you use the method that is the simplest for you, and that will help you to be able to answer the questions. Now, if we were to move, we can say now, how will each of the following be affected if light of frequency, this light of frequency 12,54 times 10 to the power 14 hertz, but of higher intensity? You see, this question of intensity is almost always there in your paper. So it's important that you have it and you always remember what you talked about. When you say intensity, you're talking about brightness. When it increases, the current or the number of photoelectrons, ejected photoelectrons per unit time will increase. So you remember that one to say, okay, this one is what happens, so that when the question comes, you're able to remember. The value of x, what is x? We said x is kinetic energy. And we said kinetic energy, remember with kinetic energy, we said it increases with increasing frequency. Keep it there to say when you increase the kinetic energy, you increase is when the kinetic energy increase with increase in frequency. So frequency is not frequency that we increased here, we increase intensity, which means now the value of if the value of x, what will happen? Don't say remain the same. You will find that their learners, when they are given a question like this one, they will say remain the same. But remain the same is not one of the options that were given. If we look at the options that were given increases, decreases, or no effect. So you are restricted to, so your answer must be one of these. So because we're increasing brightness, it affects the number of photons and the number of photoelectrons that will be ejected. It does not affect the kinetic energy, which is x. So there will be no effect because we have increased intensity, not frequency. Now, what will happen to the number of photoelectrons emitted per unit time? You see, I'm happy because you can see we refer to that as number of photoelectrons emitted per unit time. Even the language is of importance in this section to say when we talk about them, you will talk about the number of electrons or number of photoelectrons emitted per unit time, so that at least we are consistent with how we answer this type of questions. So what will happen when we increase? Remember we said biggie. We said when we increase the brightness increases with current increases as well. So current is the number of electrons. So you can see that the number of photoelectrons emitted per unit time, definitely it increases with increasing brightness or increasing intensity. So when increase intensity, we're increasing the number of photoelectrons emitted per unit time. So you see, if these things that we have discussed here, you got hold of them, I'm telling you, you're going to enjoy a lot of these questions and you will get many marks. Remember, we're thinking about plus or minus 13 marks that we're expecting that you will get from this question. And then you just have to practice as many questions so that you are not shocked when you come across questions in the exam. Now, metal B has a larger wave function than metal A, and then you are able now to say redraw the graph above in the answer book. Do not include the values on the axis. Label this graph as A. On the same set of axes, sketch the graph of metal B. So you had that one, which is now your graph for A. It was like that, and then they're saying no, you can redraw and write your EK and your frequency as well. You redraw the graph there, and then do not include the labels. But what happens is that now they are saying now what will happen? How will each of the following affect? Now the saying metal has a larger work function. When it has a larger work function than metal A, so you see now remember. The relationship there, E equals to that plus that. We are saying when the work function increases, EK decreases. You get that? So more of the energy will go to work function. So metal B has a larger work function. If it has a larger work function, it means it has a larger threshold frequency. Remember, work function is directly proportional to threshold frequency. So definitely the threshold frequency for this one with a higher work function, it will have a higher threshold frequency, hence higher, it means more than 5. So it must be this side, the other graph that you are going to draw, it must be this side of your graph. So it must be somewhere there. They said don't include the values. The main thing they wanted to see your EK there in joules and your frequency in terms of hertz here. And then you are able to show that it will be on the other side of A. B will be this side because now it has a larger work function. Larger work function means larger threshold frequency, and threshold frequency increases on this line when you move to the right. So you're able to do that and be able to get your mark. Now, your homework, you can take a picture. You will do the homework. You are given the apparatus as illustrated. Simplified diagram below is used to demonstrate the photoelectric effect. And then the first question says, define the term photoelectric effect. And then You had 3.1.2 as well, and then you had 3.1.3. So those are your questions, which is with about 11 marks. So we're saying on your own, take a picture, be able to do that exercise, and it will help you as you consolidate what we have done today. I hope you have really gained a lot, and it will help you going forward. So you will do that activity. Sorry, just to say, as we complete our lesson, to say you have heard and understood what we were doing, and I'm hoping that you will always remember that we are talking photoelectric effect, we are talking threshold frequency, we are talking as well your work function, we are talking as well your atomic absorption spectrum. I've spent some time there talking about it. We're talking about emission absorption spectrum. Hoping that you remember all of those. Remember the Doppler effect equation as well, which we said that's how it goes. Remember, we talked about all that. So you will have appreciation of all that which we have done today. So the main thing that we are emphasizing is that go and do questions, and do as many questions as you can, and then we will be able to say you are ready for photoelectric effect. You have to definitely collect these marks and practice. You know, when you practice in such a way that all the question papers that are supposed to do question 10, you take all of them, you practice. After that, you always go to the memo marking guideline and you check your answers, whether they are correct or wrong, and then you are able to get the right and be able to pass. And do the homework, as I indicated that we have the homework, be able to do it as well. And then we are saying that if you have done all that, you will be ready in terms of this topic. And we are saying just in time, on the 8th of August 2025 at 2:30 to 4 o'clock. Now we are moving to electrochemistry. We'll be talking now your oxidation and reduction reactions. And with that, I would like to say thank you. And as we always do when we close, anyone who has never made a mistake has never tried something new. That is Albert Einstein. Thank you very much.